Hi and welcome to this video. This video is the fourth video in the series about the concurrency points. So this one is going to deal with the altitudes. So first we start out with a definition again. The altitude is the perpendicular segment from a vertex to the line containing the opposite side. So if I draw a triangle, the altitude is going to go from the vertex and then it just has to be perpendicular to the other side. So maybe it comes over here and it's perpendicular. So that's an altitude. So if you draw the altitudes of a triangle, they are all concurrent. And there's no special properties it listed like the other one, but there is something we want to show you about it and something you need to know about it. So the altitudes, so let's name this one. This one is the altitude concurrency theorem. And the altitudes are concurrent at a point that's called the orthocenter. So one last cute little mnemonic. For this one we have altos or orthos. So the altitudes form the orthocenter. So again, let me show you the altitudes. There they are. Now if I move my circle around, let's first see if it'll go outside. It does. So depending on where I make my triangle, I can make my orthocenter inside and I can make it outside. I can also make it so that it's on the triangle. In this case, it'll be on the right angle. So if I make a right angle, then the orthocenter will be right on that right angle, which makes sense because if it's a right triangle, the altitudes will be two of the sides of the triangle. Now, if I make my triangle acute, the orthocenter will be inside, and if I make it obtuse, it'll be outside. Now for this one, it's another one that says center, so we've got orthocenter. So what I want to show you is why it's called, has center in it, and it's kind of an interesting reason why it has center. So what I'm going to do is I'm going to draw 3 segments and make a triangle. So I'm going to take all the places where the altitudes meet up with the sides of the triangle. And what I get is another triangle. And that triangle has a special name. It's called the orthogonal triangle. Okay, so the orthogonal triangle is made up of the places where the altitudes intersect the sides of the triangle. So let me get rid of that so that I can move it around some more. Now, if you notice, if I move the triangle around, that orthocenter stays inside that orthogonal triangle. But it's even better than that. Now, one important thing to notice is if it's an obtuse triangle, then I don't have the orthogonal triangle. So if I make it an acute triangle, not only does that concurrency point, the orthocenter, stay inside the orthogonal triangle, but it actually is the incenter of that orthogonal triangle. So let me show you. So in order to do an incenter, I have to do a perpendicular line. So let me construct a perpendicular line. So there's my perpendicular line. And then I'm also going to move it again so that I can see it easily. There it is. And now I'm going to make a circle that goes from the orthocenter to one of the sides where that perpendicular line meets the sides of the orthogonal triangle. So there we go. And now if you notice, what happens is if I move this around, not only does that orthocenter stay inside the triangle, but it is actually the incenter of the orthogonal triangle. So here's what you need to know for that. One is you need to know how to draw the orthogonal triangle, so make sure you know it's made up of the places where the altitudes intersect the sides of the triangle. And then also you need to know that the orthocenter is the incenter of the orthogonal triangle. Other than that, we don't have any special properties of the orthocenter. Make sure you know that it can occur outside and inside and when it occurs on the triangle. So the last thing I want to show you is a special property of 3 of the concurrency points. So what I'm going to do is down here I'm going to turn on all 4 of the points. So I have the circumcenter, the centroid, the incenter, and the orthocenter. And what I want to do is I want to move the triangle around. So a couple things to notice is that as I move these around, two of them always stay inside, the incenter and the centroid. And two of them can go outside, the circumcenter and the orthocenter. Now, if you also take a look at them, three of them appear to be staying in a collinear line. So the incenter is kind of a little off center from the rest, but the circumcenter, the centroid, and the orthocenter are staying in a pretty solid line. So what I'm going to do is I'm going to turn on that line. And that line is called Euler's line. So there it is. And Euler's line is made up of three of the concurrency points, the orthocenter, the centroid, and the circumcenter. A nice, easy way to remember it used to be more beneficial in past years, but there used to be a program called the OC, and so students like to remember it as the OCC. So the orthocenter, the centroid, and the circumcenter. Some people just remember it's the two C ones and the O one, but you do need to know which ones form the Euler's line. The only one that doesn't is the incenter. Also, if I play around with it, you notice that I can get some of these to kind of line up. So now, actually, I have all four of them that appear on the line. So one of the things we're going to talk about is when are all four of them form a straight line, and there's kind of a hint right there if you take a look at it. There's something special about that triangle, all four of them. And then I can also get all four of them to, there we go, to coincide. So that's pretty close. Now, if you take a look at the angle measure, there's kind of a hint about when they all four of them coincide. So think about what would the triangle possess for all four of them to coincide. And that's it for Euler's line. Thank you for watching. Have a great day.